Hey guys and girls, happy Friday to me, happy Monday to you all. Wanted to get you in the lab today. Hopefully, if all went to plan. During the first part of the big block we had, it led you guys through some conversation about rates of reaction. And we talked about the different things that can affect the rate of the reaction. Concentration is a big factor, catalyst, temperature, all contributing to how quickly two substances will react with each other to create some amount of product. The other one is the phase that the reactant exists in. If they're homogeneous, the same phase, they interact with each other much more quickly. And all that's controlled by particle theory. All right, the more similar the particles are, the easier they can interact. The faster the particles are moving, the more often they collide, the faster the reaction tends to occur. All right, and that's a big theme throughout all of this chapter. Right, and that's what they call kinetics. So the first lab we're going to take a look at here is how do we determine how fast the reaction goes? How do they know that your body will break down 200 milligrams of aspirin in 4 hours so that you can take another one? How do they know I only have to take one of these per day, whereas other medications are 2 per day? How is it they figure out how quickly reactions occur, how quickly things can disappear or appear? Right, so the idea behind the rate of reaction is if we want to get the speed, the rate the reaction occurs, you want to measure how quickly either A, a reactant disappears, or B, a reactant appears. Either is going to tell me how fast the reaction is happening. And why would we not do one over the other all the time? Some phases of products are easier to measure than others, right? Sometimes you're going to find out working with gases can be difficult. So measuring how quickly a gas disappears can be tricky. Right? Measuring how quickly it appears, not as much. Right? So it really depends on what the reaction is, who are the parties participating, and what do we do. So like I said, if we are measuring a reactant, what we are going to look at is how quickly it disappears over time. Right? And what it is that we measure will be dependent upon what the reactant looks like. If it's a product, on the other hand, we're measuring how quickly it appears over time. Now, the phase that the reactant or the product exists is controlling what the experiment looks like. If my reactant is a solid, those are pretty manageable. I simply measure what the mass change is over a span of time, how quickly we create solid, or more commonly, how quickly the solid disappears. All right, the amount of solid, because we can measure those things with a balance and time it with a watch. If it's a gas, these can be a little bit trickier. Right? We measure a gas generally created over time. Like I said, it's tough to measure how quickly a gas disappears over time because gases are tough to trap in that fashion. All right, so this is going to be what we do in part 1 of our experiment. We're going to measure how much gas gets created over a time, and that's going to tell us the rate that that gas was created at. And then lastly, if it's a solution, right, like we talked about last chapter, we measure the concentration change over time, but we really can't do that correctly, which you will find out. Right? We will measure the absorbency over time, how much light it blocks. And we do a whole different experiment for that one. All right, so today's experiment, we're going to measure solid and gas-based substances. All right, so in part 1 of this experiment here, we're going to measure some gas created over time. And the title of this lab, it says at the top, is how long would that marble statue last? Because marble is a chemical compound. It is calcium carbonate. So what we are going to do is we're going to take an amount of calcium carbonate and we're going to put it into the bottom of 125 milliliter Erlenmeyer flask. So we know we've got calcium carbonate. Then what I'm going to do is I'm going to dump 6 molar hydrochloric acid into that container. We're going to measure the amount of this and this, but we don't even really need those things, because what I'm really going to use to determine my rate is how much gas I create over time. All right, so I don't even care all that much about the amount of the chips, even though I'll tell you it's 0.5, and the amount of the acid, even though I'll tell you it's 10 milliliters. Because what we're going to do is we're going to harness one of the products. Right? So if we set up that reaction, you're going to get a double replacement. You'll get calcium chloride, and you're going to get hydrogen carbonate, H2CO3. But if you remember, hydrogen carbonate on your solubility list is one of our 3 specials. It is too unstable most of the time to exist this way. So as soon as it gets created, it decomposes into H2O and CO2 gas. And that is the gas that is going to get released that we are going to trap. Right? So what we're going to do is we're going to mix those things in this flask. The reaction there is going to be occurring. So you're going to have liquid in there at the end. What's it going to look like in the liquid? Right? We're going to have Ca+2 ions floating around because the CaCl2 is soluble. We're going to have Cl- ions floating around. Right? Obviously, there's going to be water in there from the decomposition, but the big one that we're trying to exploit is the release of the carbon dioxide gas. Right? That gas is going to get created, and what we're going to do is have a stopper on top of this guy attached to a syringe. And that syringe is going to be plugged into the Erlenmeyer flask. Right? So it's going to start down here with no gas, but as the CO2 gets created and it's less dense, it's going to go up in, and it is going to push the cylinder piston up. And that's what we're going to measure, how much gas we collect in this cylinder over an amount of time. All right, so I'll show you the beginning part of that reaction, and then you'll find out that in the procedure that I attached to you guys, the full data table will be pre-filled in, right? We don't have to watch it for the full 20 minutes. I just want you to see the process of how that's occurring. All right, so let me take you to the back, show you that, and then we'll double back up front and take a look at part 2 of the experiment where we look at mass differential. All right, so here's my setup. All right. So I've got my syringe here. All right, notice I've got a stopper and it's got a valve on here. All right, I would always tell you guys in class, make sure that that valve, which is called the stopcock, is open, because we want to make sure that the gas can push up into here. And when we start creating gas, it's going to push this cylinder piston up. The more gas you create, the further up it goes. And we're going to monitor what that is over a span of time as we go through. All right, so the first thing it tells me to do is to measure out roughly 0.5 grams of my marble chips, which remember is the calcium carbonate. All right, so I come over here. It's marble, so it's easy to touch. Right? They say it takes roughly 3 chips. So you would want to kind of pick on the smaller ones. All right, so there's my 0.5. Okay, I take those and I drop them into my Erlenmeyer flask. Then what I'm going to do is I'm going to take 10 milliliters of my 6 molar hydrochloric acid. Right, so I'm going to measure that out. And I'm going to add that to the flask. And when I do that, I'm going to have to quickly put the top on. Now, when I put the top on, I'm going to do it fast. I won't have time to talk about it. I'm going to plug the top in. I'm going to give this a pull and a quick push, all right, just to break the coefficient of friction. right? So that the gas can start pushing this relatively easily. I don't want it to have to overcome, right, the beginning part where it's sticking. Otherwise, sometimes it stays in the bottom. All right, so I have to do that here. Measure out my 10. Bit more. Okay. All right, so I've got my 10 milliliters of my acid there. All right, and now I'm ready to initiate this reaction. All right, so we're going to go ahead and do that. And right away, you can even see it fizzing. That on. Up, push down. You guys can see that we've got some fizzing action here in the bottom. Right, that's the acid reacting with the calcium carbonate. Right, we're making the calcium chloride. Those ions are just dissolving and staying in the liquid there. Right, we're creating the hydrogen carbonate, which is decomposing into the water and the CO2 gas. And the CO2 gas is what we're going to try to catch. Right, in the data table, it has us measure this every 2 minutes for a span of 20 minutes. All right, so I'm going to let that run just for a minute so you can kind of see how it gets going. Every once in a while, you want to give it a stir. You can see we're collecting the gas. Right? Like I said, you give it a little push, break that friction, and you can see the gas keeps pushing up into the container. All right, that would be our first 2-minute mark. All right. And I'm going to read you guys the results, all right, from that so that you guys can fill in your data table, all right, as we go through that. All right. So for your 2-minute mark, we would have gathered, right, 44 milliliters. At the 4-minute mark, we would have gathered, and I just want to make sure this syncs up with your table. All right, at the 4-minute mark, we would have gathered 82 milliliters. At the 6-minute mark, we would have gathered 100 milliliters. At the 8-minute mark, we would have gathered 106 milliliters. At the 10-minute mark, it's 110 milliliters. And then at 12, it's 112 milliliters. At 14, it stayed at 112. At 16, it stayed at 112. At 18, it stayed at 112. And at 20, it stayed at 112 milliliters. All right, and what that tells us is when we get that leveling off effect, we know the reaction has ceased, right? We aren't creating any more gas, right? So we aren't increasing the volume inside of our cylinder. All right, so when you stop creating new gas, that means the rate of the reaction is 0 because the reaction is over. All right, so that's what's going on in part 1. And like I said, I'll toss those into that table for you. But just in case something glitches or something along those lines, I wanted you guys to have those numbers in the video as well. Okay. All right, so taking you back up front for a quick moment, talk you through part 2 of the experiment. And then we'll go back and I'll show you the setup and we'll get you those numbers. So in part 2 of the experiment, we're going to measure something different. We're not measuring a product being created over time like we did for part 1 with the CO2. We're going to measure how a reactant disappears over time. All right, we're going to measure the disappearance of CaCO3 over an amount of time. And because CaCO3 is a solid, that means it's mass driven. We can monitor its mass. So this one isn't particularly exciting, but that doesn't mean it's not effective, right? We're going to take our balance. All right, we're going to put a flask on it. Right, it's going to have some amount of CaCO3. We'll measure that out. We'll put it in. It's supposed to be about 1.25 grams. Right, then we're going to dump in different acid this time. We don't need the reaction to generate quite as much gas, so we don't have to use as potent of the HCl. We use 3 molar HCl. And then once we dump that in there, we are going to measure the initial mass. Right? And we need the liquid to be in there as well. Otherwise, new added mass will be because of the liquid. Right? So the initial mass isn't of the CaCO3. It's of the CaCO3 and the HCl. But between the two of those, based on what's happening, the CaCO3, the chip, that's what's going to get decomposed. It's going to get broken down. So the only thing disappearing is the solid. So what we're going to do is we're going to measure a series of masses. And it will be no surprise that the masses will get lower and lower and lower. And the missing mass is due to the calcium carbonate, the marble chip that is disappearing. All right, and this is basically the process that happens when acid rain rains on a marble statue, right, if it is untreated. All right, so that mass is going to get lower and lower and lower, and then what we're going to do is measure the missing mass, which is calcium carbonate, over time, and now you know how quickly the calcium carbonate is reacting away. All right, so like I said, that setup isn't anything crazy, but I'll show it to you. And then I'll get you guys working on your labs. All right. All right, so here you have your balance. What we would do is we would simply take our flask, we'd put it on our balance. It would have the HCl in it. It would have the marble chips in it. We'd record that mass value. And as it's fizzing and as it's fizzing and as it's fizzing, it would get less and less and less and less. And we would monitor what the mass drop was over time. And that's what data table 2 is all about. And like I said, in data table 2, we're looking at the total mass of the contents in the flask. And then notice it's saying cumulative mass lost in grams in your data table. That is representative of the CaCO3 disappearing. All right. And what you're going to be able to do then is you're going to be able to plot a graph. All right. And what you're going to find out is that both of your graphs are going to take this arcing shape and level off, right? Because like I said in class prior to this starting, any reactions fastest portion is always at the beginning because you have the highest concentrations of the substances. Now, a solid won't make much difference because it doesn't have a concentration. It will just keep reacting until it's gone. All right, so hopefully this helps you guys. All right, I'll break you guys off into your lab groups, and you guys can start working on your lab report.